Lecture 22, Algorithms and Heuristics. We can learn a lot about how people think by looking at the mistakes that they make. For example, when Justice Gray classified a tomato as a vegetable rather than a fruit, and the other 8 members of the United States Supreme Court agreed with him, he was actually doing something quite interesting. Notice that he didn't compare the features of the tomato to the defining features of either category, either fruit or vegetable. Rather, he focused on characteristic features, features that are correlated with category membership, but not defining of any particular category. For example, that tomatoes are served with dinner, but not as dessert. And he compared tomatoes to other exemplars of the vegetable category, such as potatoes and carrots and lettuce. This is not how the logicians would have us define categories and categorize objects. So again, the way we reason about categories departs radically from the prescriptions of the logicians. And we're going to see more such examples in this lecture, as we try to build a descriptive account that is faithful to how people actually reason, make judgments, decisions, and solve problems. For example, one popular view of human reasoning is that it proceeds by means of algorithms. An algorithm is a kind of recipe for thinking, for reasoning, for problem solving, for making a decision. If you want to make a particular dish for dinner, you look up a recipe which specifies the necessary ingredients and the amounts you need of each and the order in which you combine them, and you just follow the steps 1, 2, 3, and out comes a dinner. Similarly, we can define an algorithm, a term that comes over to us from mathematics, as a set of logical, systematic rules whose application will inevitably solve some problem. If you apply the correct algorithm and you apply the algorithm correctly, you are guaranteed to reach the correct answer. You'll never make a mistake. For example, here's a kind of algorithm for estimating some quantity. Of course, you could always count it or weigh it and get an exact number, but sometimes that's not practical. For example, the United States Constitution specifies that every 10 years there has to be a census of the population, which it describes as an enumeration, implying that we have to actually have a physical head count. But that's a very expensive process. It takes a long time, it's very involved, and there are reasons for thinking that even a head count isn't completely accurate. So there have been proposals from time to time that we should simply estimate the population of the United States and let that be good enough. And the fact of the matter is, we know how to do this because there are algorithms, statistical algorithms, that tell us how to make valid estimates of various kinds of quantities, including the population of a country. First, we have to draw a representative sample of the population. This might be a random sample, or it might be stratified in some way, like drawing a random sample of each of the states instead of the random sample of the country as a whole. And then we extrapolate from this sample to the population at large. And again, we know how to do this. Since the 19th century, statisticians and other mathematicians, psychologists and other social scientists have developed rules for statistical inference and hypothesis testing that allow us to do just this and allow us to do it with a great deal of accuracy. Our estimates are as accurate as they are precisely because we follow the algorithms, and algorithms, if properly applied, are guaranteed not to lead us to make a mistake. In the domain of problem solving, there's an algorithm known as means end analysis that works for all sorts of problems. But what do we mean by a problem? Well, it turns out that in psychological terms, all problems have 4 elements. First, there are the givens, the statement of the problem itself. Then the goals, what's to be achieved when the problem is solved. Third, there are transformations that get you from your start state, the givens, to your end state, the goals. And then finally, there are obstacles along the way. All problems involve some sort of obstacle. If there weren't obstacles to the transformations, there wouldn't be any problem to be solved. Means-end analysis as an algorithm for human problem solving begins with just forming a mental representation of both the current state and the goal state, where you are now and where you want to get to. Then you calculate the difference, and then you take some step that will reduce that difference by some amount. And then you simply repeat the process. You represent your new current state and your final goal state, calculate the difference again, take a step that will reduce the difference, and repeat that over and over and over again until the difference is zero and you've achieved your goal. This is an algorithm that's guaranteed to solve a problem. It looks very simple, and it is, but that doesn't mean it doesn't work. As an example of how means-end analysis and problem-solving works, consider a classic problem known as the Tower of Hanoi. Legend has it that in Hanoi there's a temple in which there's a tower of 64 sacred golden discs. The discs are stacked on top of each other, with the largest on the bottom and the smallest on the top. The monks of the temple must move the discs from one location to another, one at a time, such that a larger disc is never placed on top of a smaller disc. Besides the original location and the new location, there's only one other place in the temple sacred enough to hold the discs. And the legend holds that before the monks complete the task, their temple will crumble into dust and the world will end. So here we have all the elements of a problem. We're given 64 disks stacked in a particular way in a particular place. And the goal is to move the disks so that they're stacked in the same way in another place. And there are a couple of obstacles. First, there's a constraint on how the disks can be stacked. There can never be a large disk on top of a smaller disk. And second, there's only one intermediate location where any disks can be held. Of course, there isn't such a temple, at least not to my knowledge. This is just a puzzle. But you might ask, gee, how do you do this? How many moves would the task require, and how long would it take? Here's a simplified version of the Tower of Hanoi with just 3 disks, but otherwise the same constraints. There are 3 locations, and you can't put a large disk on top of a smaller disk. Take a couple of moments and figure out how to solve the problem. And then go to the next slide. There. You move the blue disk onto the rightmost peg, then the purple disk onto the middle peg, then the blue disk onto the middle peg, then the red disk onto the rightmost peg, then the blue disk onto the leftmost peg, the purple disk onto the rightmost peg, and then finally the blue disk on top to finish. At each step along the way, you looked at your current state, your goal state, you calculated the difference between them, and you took a step to reduce the difference, and you just repeated that process over and over and over again until you were done. Returning to the original Tower of Hanoi problem, moving 64 disks in just this manner would require 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709,551,615 moves, which is a lot of moves. At the rate of 1 move per second, this would take more than 5 billion years. That's older than the age of the Earth. And assuming that monks move a little bit more slowly than this, it appears we're safe for now. A similar problem is now known as the Hobbits and Orcs problem. In the 19th century, it was known as the Missionaries and Cannibals problem, but it has a long history. It was originally devised by Alcuin a medieval English monk who died in the early 9th century. Anyway, in the modern version, we have 3 hobbits and 3 orcs on one side of a river. You probably remember the hobbits and orcs from J.R.R. Tolkien's Lord of the Rings. Orcs eat hobbits when they outnumber them. The creatures have a boat on their side of the river that's capable of carrying 2 creatures at a time across the river. And the goal is to transport all 6 creatures to the other side of the river, bearing in mind that at no point on either side of the river can orcs outnumber hobbits, because if they did, they'd eat them. And you set up this problem and solve it in exactly the same way, using means end analysis. You're given 3 hobbits and 3 orcs on one side of the river. That's your beginning state, your present state. You're also given a boat that can hold 2 creatures at a time. The goal state is to get the 3 hobbits and the 3 orcs over to the other side of the river. The transformation involves the boat, and the obstacle is that orcs can never outnumber hobbits. You can solve this problem using means end analysis exactly the way you solved the Tower of Hanoi problem, and after you finish the lecture, you might try to do it. I'll warn you though, there's a trick. Means end analysis is a perfect algorithm for solving a particular class of problems known as well-defined problems. Well-defined problems are those that are completely specified in terms of the initial conditions of the problem, the goal to be achieved, and the intermediate operations to be performed. Elementary algebra is a good example of a well-defined problem. If I give you an equation like 3x plus 3 equals 12, and I ask you to solve for x, there's a set of intermediate operations that'll get you the correct solution. You subtract 3 from each side of the equation, and then you divide each side of the equation by 3. Well-defined problems are those in which there is only one possible representation of a problem, and thus only one correct solution. And in this case, algorithm will give you that correct solution every time. Unfortunately, there are other problems that are not so well defined. In fact, we call them ill-defined problems. And they're defined as problems that are incompletely specified with respect to the initial conditions, or the goals, or the intermediate operations, or some combination of these. An example of an ill-defined problem might be an equation like 3x plus 3y equals 12. And I ask you again to solve for x. Here, the usual algorithm won't help. This is because there are many possible representations of the problem, and thus many possible correct solutions. While well-defined problems can be solved through the application of some algorithm, there just aren't any algorithms that are available to solve ill-defined problems. Ill-defined problems, in turn, are an example of a wider set of problems, collectively known as conditions of uncertainty. Uncertainty occurs first when a problem is ill-defined, when there are many possible representations of the problem, and thus more than one possible solution. But uncertainty can occur under other conditions as well. For example, a problem may be well defined in some formal sense, but you simply don't know what the algorithm is. Or you may know what the algorithm is, but you may have insufficient information to apply the algorithm. Or you may have insufficient opportunity to apply the algorithm. These conditions are collectively known as judgment under uncertainty. Under these circumstances, when algorithms cannot be applied, we have to do something else. For one reason or another, the algorithm is just not going to get us to the solution to the problem. So what do we do under conditions of uncertainty? We have to do something. We can't just not solve the problem. Under these circumstances, when algorithms cannot be applied, it appears that people rely on what are known as judgment heuristics, shortcuts or rules of thumb that bypass the logical rules that are represented by problem-solving algorithms. The term judgment heuristics was introduced by Daniel Kahneman and Amos Tversky in some collaborative work that the two began in the 1970s. Kahneman and Tversky's work on judgment heuristics has revolutionized our understanding of human judgment and decision-making, and has had far-ranging implications for things like economic decision-making. In recognition of their achievement, Daniel Kahneman shared the Nobel Prize in Economics for 2002. Unfortunately, Tversky could not share in the prize because he had died, unfortunately, and the Nobel Prize rules don't permit the prize to go to individuals who are not living. But Kahneman was very clear in his acceptance of the award that his work had been collaborative with Tversky. Anyway, these judgment heuristics, these shortcuts, these rules of thumb, bypass logical rules and thus permit us to make judgments under conditions of uncertainty. Which is great, except that precisely because judgment heuristics bypass the logical rules of reasoning, their use also increases the probability of making a judgment error. Remember, using the appropriate algorithm guarantees that you'll get the right answer every time, precisely because the algorithm is based on logical rules of inference. But if you do anything else, it's possible that you're going to make a mistake. Judgment heuristics are absolutely necessary for making judgments under conditions of uncertainty, but it turns out that people also use these heuristics when they make judgments under conditions of certainty, when the problem is well defined. That's when they can make errors, and in fact we're able to infer what judgment heuristics people are using from the errors they make in judgment. In much the same way that we inferred the prototype or exemplar structure of mental categories from errors like Justice Gray's. In their work together, Tversky and Kahneman identified 4 judgment heuristics that are commonly used in reasoning about various kinds of problems: representativeness, availability, simulation, and anchoring and adjustment. Let's take a look at each of these heuristics in action, see how they work, and how they can lead people into making mistakes in judgment and decision making. The first of these is the representativeness heuristic, commonly employed in categorization and other judgments of similarity. It's also employed in judging the probability of a forthcoming event and in making judgments of causality. So you can see the representativeness heuristic is a really important heuristic. It applies in lots of different domains. And we can see it in operation when we look at some of the errors that people make in reasoning. For example, consider the birth problem. In families of 6 children, which is the most likely sequence of boys and girls? A girl followed by a boy, followed by a girl, then 2 boys, and finally a girl? Or 3 boys in a row, followed by 3 girls in a row? Or a boy followed by a girl, followed by 4 boys in a row? Which is the most likely sequence of boys and girls? Kahneman and Tversky found that most people choose the first sequence, a girl followed by a boy, then a girl, then a boy, another boy, and a girl. They reject the third sequence on the grounds that if sex is determined randomly, there ought to be half boys and half girls, not just a single girl. And they reject the second sequence on the grounds that boys and girls should be more or less randomly interspersed. Put another way, they know that a baby's sex is determined randomly, and the first sequence looks more random than the others. In fact, the probabilities attached to each of these sequences are precisely identical. Consider that the probability of any particular newborn being a boy is 1 out of 2, half and half, and that these probabilities are independent of each other, essentially independent of each other for our purposes. Therefore, the probability of a sequence like girl, boy, girl, boy, boy, girl is about 15 chances out of 1,000. The probability of 3 boys followed by 3 girls is again about 15 chances, 16 chances out of 1,000. And the probability of a boy and a girl followed by 4 boys is again exactly the same, 15 or 16 chances out of 1,000. This is how the probabilities work. But knowing that, the first sequence, girl boy, boy, girl, just looks more likely. It looks more like a random sequence, and that's the point. Here's another example, what's known as the gambler's fallacy. On a fair roulette wheel, half the numbers are red and half the numbers are black. Now, which of the following runs seems most likely to end with a red number? Most people, except maybe people who have just been exposed to the birth problem, which we've just discussed, choose the third sequence. Number 1 looks random and unpredictable. A red followed by a black, then 2 reds, then a black, a red, and a black. You don't really know what's going to happen next. People are prepared to accept a relatively short run of blacks, as in the second example, but they expect that following a long run of blacks, the random process will have to somehow straighten out and produce a red. But the probability of getting a black number is 1 out of 2, and the probability of getting a red number is also 1 out of 2, and these probabilities are strictly independent. Therefore, on any particular spin of the wheel, the probability of it stopping on a red number is 1 out of 2, regardless of what's happened before. But a long run of blacks, or a long run of reds for that matter, doesn't fit our intuitive notion of randomness, and so we expect that a red will come up soon to make the sequence appear more random. The gambler's fallacy actually relates to the birth problem in an interesting way. Some couples, after producing a string of all girls or all boys, decide to try one more time to get a child of the opposite sex. Even though the sex of this new child is completely independent of the sexes of their previous children, these couples seem to think that the series will somehow straighten itself out or even itself out, so that their own particular family will look more like a random assortment of girls and boys. Of course, this tactic fails about 50% of the time. All of these errors illustrate the representativeness heuristic, which may be defined as a judgment strategy whereby judgments are based on the extent to which an event is similar in its essential features to its parent population, or alternatively on the extent to which an event reflects the salient features of its presumed generating process. If we know a process is random, like the outcome of a spin of a roulette wheel or the outcome of a conception, then we expect the output of that process to look random, and we judge outputs that look random to be more likely than outputs that don't. Now, this isn't a bad strategy. Judgment by resemblance is essentially how we make judgments of similarity and judgments of category membership. However, applying the representativeness heuristic can sometimes lead to judgmental errors when we fail to appreciate the base rates of events, when we fail to appreciate the fact that births are essentially independent of each other and spins of a roulette wheel are essentially independent of each other. We have to correct for representativeness by taking into account the base rates of a process or the prior probabilities. Justice Gray's classification of a tomato as a vegetable rather than as a fruit illustrates the representativeness heuristic in categorization. From his point of view, tomatoes just don't resemble fruits, at least insofar as their functions as foods are concerned. Rather, they resemble vegetables. Tomatoes have features resembling those of other vegetables, but they don't have features resembling those of other fruits. Put another way, a tomato's not a representative fruit, but it is a representative vegetable. The representativeness heuristic can also be used to make judgments about causality, cause and effect. The general idea here is that people assume that there's some kind of resemblance between a cause and its effect. So when they see something happen, and they want to know what caused it, they look for something similar in the environment. So, for example, many people oppose sex education in the schools and the availability of birth control for minors on the assumption that sex education and birth control will cause premature sexual activity, and thus things like teenage pregnancy and abortion. The idea is that sexy effects have sexy causes. But in fact, sex education and birth controls seem to keep teenage pregnancy and abortion down. It doesn't have much effect on the rate of teenage sex, but it does have an effect on pregnancy and abortion. Similarly, many people oppose violence on television, movies, and video games because they believe that it causes people to behave violently in society. This idea is intuitively appealing, and there is a correlation between exposure to media violence and displays of violent behavior, but in fact it's been very difficult to prove that violence in the media actually causes violent behavior. And then finally, many people promote music and arts education in the schools because they believe that these programs enhance student achievement in other domains, such as math and science. And it's certainly true that music and art education make people look smarter, and they're certainly smarter about music and art. There's no evidence for any causal relationship between these kinds of programs and academic excellence. In fact, the true situation may well be the reverse, that schools with a large proportion of high-performing students are forced to offer music and arts programs as well as the basics. But one way or another, these public policy positions are all examples of the intuitive idea that like causes like, and that's what the representativeness heuristic is all about. Another judgment heuristic, known as the availability heuristic, is often employed in making judgments of frequency and probability. Here's an example of the availability heuristic at work known as the word problem. In this experiment, Kahneman and Tversky asked subjects to estimate which was greater, the number of words in English that begin with the letter K or the number of English words that have K as their third letter. And then they asked subjects to repeat those estimates for other letters like L, N, R, and V. To get a sense of how subjects did this experiment, just take a couple of moments to jot down all the words you can think of that begin with the letter K. Start now. Okay, now stop. And now jot down as many words as you can think of that have the letter K as their third letter. Start now. Okay, stop. The outcome of the experiment was that across the 5 letters, most people, about 70% of the subjects tested, estimated that there were more words that had those letters as their first letter compared to the third letter. Only about 30% of subjects made the reverse judgment. But in fact, for these particular consonants, there are many more words that have the consonant as their third letter than the first, a ratio of roughly 2 to 3. That is, there are about half again as many words that have these letters as their third letter than there are have the letters as their first letter. The problem is it's easier to think of words that begin with a letter than to think of words that have that letter in their third position. We base our judgments of frequency on the ease with which we can retrieve relevant information, and that's exactly what the availability heuristic is all about. Here's another example, known as the committee problem. Given a group of 10 people, how many different committees can be formed consisting of 2 individuals? That was the question posed to one group of subjects. Another group of subjects was asked a similar question but with a different number. How many different committees of 8 people can you compose? The result of the experiment is that most people estimate that you can form lots of committees of 2 out of a group of 10, and only a relatively few committees of 8 out of a group of 10. But, of course, every committee of 2 automatically creates another committee, if you will, consisting of the 8 people remaining out of the original group of 10. 10 minus 2 is 8. Mathematically, the number of committees of k people that can be formed from a group of n people is given by something called the binomial coefficient. For committees of 2, you want to know how many groups there are of 10 objects taken 2 at a time. And for committees of 8, you want to know how many groups there are of 10 objects taken 8 at a time. And the answer is 45 in each case. Again, from a group of 10 people, every time you create a committee of 2, you automatically create another committee of 8 of those who remain. But if you try this yourself, especially if you do it in your head, you'll find that it's really easy to generate lots of unique combinations of 2 people, 1 and 2, 2 and 3, 3 and 4, 5 and 6, and so on. By contrast, it's harder to generate unique combinations of 8 people, 1, 2, 3, 4, 5, 6, 7, and 8, and 2, 3, 4, 5, 6, 7, 8, 9, 3, 4, 5, 6, 7, 8, 9, 10, and so on, and pretty quickly you get lost. You lose track of where you are. It's easy to generate committees of 2, easier than to generate committees of 8, so people think you can generate lots of committees of 2 and not so many committees of 8. The judgment is being based on the ease of generating instances. So the availability heuristic is used when people base their judgments on the ease with which instances or examples can be brought to mind. And of course, that's not a very bad strategy. Obviously, there ought to be a relationship between the frequency with which something occurs and the availability or the accessibility of that item in memory. The problem is that the availability heuristic is just based on availability. It ignores factors other than frequency that can affect availability. And that's where you start making mistakes. The simulation heuristic is related to availability, but there's a difference. Like availability, it's used to make estimates of probability, but it's also sometimes used to make judgments of causality. Here's an example of the simulation heuristic at work known as the undoing problem. Imagine that there are 2 different travelers that are heading for the airport to take 2 different flights that are scheduled to leave at the same time. That sometimes happens, especially in big airports. They meet on the curb outside their hotel and they decide to share a cab to the airport. The cab is caught in a traffic jam and the driver turns around and tells them they should expect to miss their flights. In fact, the travelers get to the airport 30 minutes late. When they arrive at their departure gates, Traveler A is told that his plane left on time, and Traveler B is told that his plane was delayed but left 5 minutes ago. And the question is, who's more upset, Traveler A or Traveler B? Here's the data. Kahneman and Tversky found that most people judge that Traveler B is going to be more upset than Traveler A, because it's easier to imagine ways in which she could have saved 5 minutes than to imagine ways in which he could have saved 30 minutes. If she had gotten out of bed when her alarm rang, or taken less time in the shower, or hadn't stopped for that donut in the hotel lobby, or checked her email, she might have taken a different cab, missed the traffic jam, and gotten to her plane on time. But of course, there's no guarantee that the imagined scenario would have occurred. No guarantee that wouldn't have done something else, or that the traffic jam might not have started earlier. In the simulation heuristic, judgments are based on the ease with which plausible scenarios can be constructed. It's similar to the availability heuristic, but here's the difference. In the availability heuristic, the judgment is based on the ease of retrieving information from memory. How many words can you think of that begin with the letter K? But in the simulation heuristic, the judgment is based on the ease with which you can imagine something happening. And of course, the problem is that there's just no guarantee that the scenario you imagine might actually have occurred. The simulation heuristic appears to lie at the root of a class of emotional states known as the counterfactual emotions. States like frustration, regret, grief, and indignation. Each of these emotional states depends on a comparison between some actual outcome and what might have been. You get frustrated not so much because your path to some goal has been blocked, but because it didn't have to be there, or because you didn't have to go that way. You could have gone some other way. You feel regret not because you did something bad, but because you could have done something else. The easier it is to imagine a plausible alternative scenario, the stronger the emotional reaction to the difference between what actually occurred and what might have been. The last of the judgment heuristics we're going to discuss is known as anchoring and adjustment. And this is a heuristic that's used in making estimates of various kinds. Here's an example of anchoring and adjustment at work known as the extrapolation problem. In this experiment, one group of subjects is asked to quickly estimate the product of a descending series of numbers like 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Another group of subjects is asked to quickly estimate the product of an ascending series of numbers like 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Tversky and Kahneman found that people who are asked to estimate the ascending sequence generally give a lower estimated product than those who are asked to estimate the descending sequence. Of course, the two products are precisely the same, 40,320. But when you estimate the ascending sequence, doing the multiplication in your head, the multiplication is easy because the intermediate results rise slowly. 1 times 2 is 2, times 3 is 6, times 4 is 24. But when you estimate the descending sequence, the intermediate results rise rapidly and the arithmetic quickly becomes very difficult to do without paper and pencil. 8 times 7 is 56, but 6 times 56 is, well, that's hard. People perform the way they do in the extrapolation problem because they extrapolate from the intermediate results, or the early results, to the final result. If the early result is low, they think the final result is going to be low as well. If the early result is high, they think the final result is going to be high. So the early result anchors the final result. Or, put another way, subjects fail to adjust the early result sufficiently. Here's another demonstration of the same effect. Tversky and Kahneman found that subjects who receive the lower initial estimate, 10%, give a lower final estimate, about 25%, compared to those who received the higher initial estimate, 65%, who give a final estimate of about 45%. So the initial estimate affects the final estimate. That's what anchoring and adjustment is all about. The initial estimate anchors the final estimate because subjects don't adjust sufficiently from the initial estimate. Amazingly enough, Tversky and Kahneman found this effect even in a variant on the experiment in which the initial estimate was given by a purely random process, such as the spin of a roulette wheel. In the anchoring and adjustment heuristic, people anchor their judgments on whatever information is available to them, such as an initial value suggested by the formulation of a problem or by some sort of partial computation. And then they adjust their judgments in the appropriate direction. However, subjects often fail to adjust sufficiently from the initial value, so that the initial value again serves as an anchor on the final estimate. In this way, final estimates are overwhelmingly influenced by initial estimates. One real-life situation in which we see anchoring and adjustment at work is in the power of first impressions. When we meet someone for the first time, our first impressions of that person tend to persist even after we've come to know the person better. In this way, our first impressions serve as an anchor on our final impressions because we adjust them insufficiently to take account of later information. Representativeness, availability, and the other heuristics are frequently used in cases of human judgment, but they can also be observed in other kinds of problem-solving activities. That shouldn't surprise us very much because, after all, making a judgment is a special kind of problem. This is especially true in ill-defined problems, where there's uncertainty about one or more of the components, but it's also true in well-defined problems where all the components of a problem are completely specified. Of course, the problem solver first has to understand the problem, and as with perception, understanding a problem requires categorization. The problem solver needs to make a judgment about the similarity between the new problem at hand and other problems that he or she's encountered before and whose solutions are known. But categorization in problem solving shares all the difficulties inherent in categorization in general. For example, people often approach problem solving through the representativeness heuristic, judging the best solution to a problem based on its superficial similarity to some other problem. And this can lead to a phenomenon known as Einstellung. Einstellung is a German word. It means something roughly like attitude and refers to the individual's inappropriate problem-solving set. For example, we can give subjects experience with a series of problems, all of which can be solved in the same way. And this will naturally induce a problem-solving set, a manner of approaching the next problem in line. Then, when presented with a problem that's superficially similar to the others, but can't be solved in the same way, or which can be solved more easily in a different way, the problem solver may focus on the inappropriate or more difficult solution suggested by the earlier problems in the series. Again, this reflects a judgment based on representativeness or superficial similarity. As another example, problem solvers can often rely on the availability heuristic, judging the best solution on the ease with which solutions to problems can be recalled. This can lead to what's known as functional fixedness. For example, if the elements of a problem all have familiar functions, but the task involves thinking of novel functions, the subject may focus on the inappropriate uses and thus fail to solve the problem. In either case, whether Einstellung is induced by representativeness or functional fixedness is induced by availability, the subject won't be able to solve the problem. In order to get unstuck, he or she has to develop a new representation of the problem. And this can happen when something occurs to break the subject's mental set, or when the subject is presented with clues about alternative functions to consider. So here we have 4 heuristics commonly used in judgment, decision-making, problem solving, reasoning of all sorts. Representativeness, availability, simulation, and anchoring and adjustment. In the years since Kahneman and Tversky initiated this line of research, lots of other judgment heuristics, problem solving heuristics have been discovered by various investigators. We don't have to talk about them all, these are just the most famous examples. In each of these cases, we know about the heuristic because of the particular kinds of errors that people make in judgment, decision-making, and problem-solving. Now, it's one thing to use judgment heuristics with ill-defined problems or under other conditions of uncertainty. But it's another thing entirely when people rely on judgment heuristics under conditions of certainty or where there are well-defined problems where algorithms will inevitably lead you to the correct answer. Even when an algorithm is available, people tend to rely on judgment heuristics instead. This empirical fact has implications for how we think about human reasoning and other aspects of human thought processes, and we'll explore these in the next lecture.